greetings of the day. In this session, we will draw a root locus for a given problem. So let us consider a problem. Sketch the root locus of a unity feedback system having g of s equal to k divided by s into s plus 2 into s plus 4. Hence, find the value of k for which the system is unstable. So here it is given, it is a unity feedback system. So unity feedback system in the sense h of s equal to 1. So the open loop transfer function g of s h of s becomes k divided by s into s plus 2 into s plus 4. So to draw the root locus, rule 1 or property says that it is symmetrical about the real axis. So we will check the property or rule 1 at the end whether we will get a symmetrical about the real axis or not. We should get and we will get. Okay. Now the second point is about the number of branches, starting point and terminating points. So we will calculate the number of open loop poles. So here n equal to 3 because denominator polynomial order is 3 s cube. So number of open loop poles equal to 3. And at what are the open loop poles? If I equate this denominator polynomial to 0, I will get 0, minus 2 and minus 4. So number of open loop poles is 3 at s equal to 0, minus 2 and minus 4. What about the number of open loop 0? Numerator polynomial is a constant. It is not a function of s, it is a constant. So number of open loop zeros m equal to 0. So number of branches is equal to maximum of n or m. So in this maximum is 3. So number of branches is 3. So all the 3 branches start from the pole s equal to 0, minus 3 and minus 4. But there are no terminating point at open loop 0. So all the 3 branches terminates at open loop 0 infinity. All the branches terminate at 0 at infinity. So the plot initial stage, we will draw the x-axis real part, y-axis imaginary part, and we will mark the poles by cross lines. So at s equal to 0, s equal to minus 2 and s equal to minus 4. Then rule number 3, which are the part of the real axis is the part of the root locus. So if I consider any point from plus infinity to starting from 0, to the right side no poles or 0 exists. So this is not a part of the root locus. Now whereas these two between 0 and minus 2, if I consider any point in this, for example minus 1, minus 0.5, minus 1.5, any point if I consider in between 0 and minus 2, from that point to the right on the real axis only one pole is exists, open loop pole. So this 1 is an odd number. So this is entire 0 to minus 2 is a part of the root locus. So that is why I have drawn using a blue color. So in between minus 2 to minus 4, if I consider the region between minus 2 to minus 4, any point if I consider to the right 1 and 2 poles are exist. So total number of poles and zeros to the right from the point is an even number. So this is not a part of the root locus. Similarly, if I consider any point starting from minus 4 to minus infinity, to the left of minus 4, any point test point if I consider, to the right 1, 2, 3 poles exist. So total number of poles and zeros together is a 3, which is an odd number. So entire left of s equal to minus 4 is a part of the root locus. And poles are the starting points, so direction is away from the poles. both. Okay, so plotting the points, poles and zeros. In this no zeros, so only poles. Then based on rule number 3, identifying the real part and assigning the direction. Next, we need to concentrate on angle of asymptote. So from the formula, angle of asymptotes phi equal to 2q plus 1 into 180 degree divided by n difference m. As I said, n difference m because n may be greater than m or m may be greater than n, where q is equal to 0, 1, 2, because it is q is varying from 0, 1, 2 up to n minus m minus 1. So here n is 3, m is 0, 3 whereas 0 is 3, minus 1 is 2. So 0, 1, 2. So when I substitute q is equal to 0, q is equal to 1, q is equal to 2, what are the angles I will get? So phi 1 is 60 degree, phi 2 is 180 degree and phi 3 is 300 degree. That means branches terminates at infinity at an angle of 60 degree, 180 degree and 300 degree. Okay. Next point is centroid, where these three asymptotes intersects on real axis. So centroid sigma is equal to, as per the formula, summation of poles minus summation of zeros divided by n difference m. So summation of poles, what are the poles? Open loop poles, 0, minus 2, minus 4. What about open loop zeros? No open loop zeros, so 0. Divided by n difference m. So minus 6 by 3, that is minus 2. So from s equal to minus 2, we need to draw these three angles, that is 60 degree, 180 degree and 300 degree. So the plot becomes, at s is equal to minus 3, I am plotting a 60 degree line. As it is not a part of the root locus, it is only asymptotic line, I am drawing it by a dotted line. So this 60 degree and 180 degree, it is negative real axis and the other one is a 300 degree. So at s equal to minus 2, that is at centroid, we are plotting the angle of asymptote 60 degree, 180 degree and 300 degrees. Next is breakaway points. So to obtain the breakaway points, we need to obtain a characteristic equation. So in general, characteristic equation of the system is 1 plus g of s h of s equal to 0. 1 plus g of s h of s equal to 0. So for this particular problem, 1 plus k divided by s into s plus 2 into s plus 4 equal to 0. So if I take the common denominator and cross multiply, I will get s into s plus 2 into s plus 4 plus k equal to 0. Right? So after obtaining the characteristic equation, we need to express k as a function of s. So by rewriting k equal to minus of this s into s plus 2 into s plus 4, that is minus of s cube plus 6s square plus 8s. So this is the expressing k as a function of s from the characteristic equation. Then differentiate k with respect to s and equate to 0. So dk by ds equal to minus s cube is 3s square, 6s square becomes 12s and 8s becomes 8 after differentiation equal to 0. So I'll get the roots are as s1 equal to s2 two roots minus 0.8453 and minus 3.1547. So these two are the roots of dk by ds. These two are the possible breakaway points. But we need to validate these breakaway points, whether it is a valid breakaway or not. So one thing is, you can validate this using a angle condition. If the angle of g of s h of s at this point is minus 180 degree, then we can say it as part of the root locus, means it is a valid. Since these are the real values, we can check from the graph plot itself. So in this minus 0.8457, it comes here, right? Minus 0.8453 comes point here, which is the part of the root locus, so it is a valid breakaway point. So minus 0.8453 is a part on the root locus, so it is a valid breakaway point. Whereas minus 3.1547, it is not a part of the root locus on the real axis, so it is not a valid breakaway point. So possible breakaway points are real values, then we need not check using an angle condition. Based on the plot only, we can confirm whether it is a valid breakaway point or not, or we can check the validity of the breakaway points. Next is intersection with imaginary axis. So to find the intersection with the imaginary axis, once again we need characteristic equation. So the characteristic equation 1 plus g of s h of s equal to 0, that means 1 plus k divided by s into s plus 2 into s plus 4 equal to 0. So characteristic polynomial, I will get it as s into s plus 2 into s plus 4 plus k, that is s cube plus 6s square plus 8s plus k equal to 0. So this is the characteristic polynomial. So to find the intersection with the imaginary axis, we need to apply Routh-Hurwitz criteria. So we need to write Routh table. So based on the Routh table, s cube is the highest order. So s cube and coefficients are s cube and s1 and 8. Then s square coefficient is 6 and constant is k. S to the power 1, I will get it as 6 into 8, 48 minus k divided by 6, and this is 0, and here I will get k. Now to find the intersection with imaginary axis, any one row should be, all the element of any one row should be 0. So by considering that at k is equal to k margin, this is 0. So to find the marginal value of k, that is k margin, I need to equate this to 0. Why I am equating this to 0? Because by equating this to 0, all the element of S1 row becomes 0. It need not be S1, s to the power 1, it can be any row, but it should make all the elements to 0. So 48 minus k margin by 6 equal to 0. By rearranging this, I will get k margin is equal to 48. So this is the marginal value, means up to 48 system is stable. After 48 system is unstable. So system is unstable for k greater than 48. Okay. Now what is the intersection with imaginary axis? Once we get any row element is 0, intersection with imaginary axis can be identified using auxiliary equation by substituting k value. So for this particular case, auxiliary equation is the row above all the element of row is 0, that is 6 s square plus k margin equal to 0. So 6 s square plus k margin is 48 equal to 0. So roots s1 and s2 I will take into this type, minus 48 by 6 minus 8. So roots are plus or minus j root 8. So intersection with imaginary axis are plus or minus j root 8 or plus or minus j 2.828. That means these two are the intersection with imaginary axis. plus j2.828 and minus j2.828 are the intersection with imaginary axis corresponding to k value 48. So last point of departure. So in this particular problem, no poles or zeros are complex. So complex poles and complex zeros are not existing, so angle of departure or arrival does not exist. So till now, whatever we have calculated, based on that we will plot the graph. So after considering all the points, if we plot, we will get the root locus like this, where one branch start from 0, another start from minus 2 like this, and at point 8,4 it is breakaway, and then intersecting at 2.828 and minus j2.828. So this is the final root locus. Similarly, we will draw the root locus for complex problems in the next session. Thank you.